In this work, we propose a safe and agile ground vehicle navigation for a 3D off-road terrain environment with consideration of the terrain-induced uncertainties while planning and tracking the path in real time. The major difficulties for navigation in 3D off-road environments first come from finding the traversable area in terms of the geometric or semantic properties of the terrain. Also, to navigate through the more safe and less conservative path, one should account for the uncertainties of vehicle maneuvers in different terrain conditions. Lastly, challenges come from the fact that the operating environment is not flat, so it has a 3D terrain topology to consider with highly nonlinear vehicle dynamics. Here we highlight our contributions by presenting the example scenario with 3 different planned paths to reach the goal. The red line path is the shortest in terms of the total travel distance, but it runs over the mud area, which causes high uncertain trajectory due to the slip. So it has a higher chance of colliding with obstacles if it's nearby. And blue line path considers both the geometric and the semantic type of traversability, so it avoids the mud area and detours the hills to make a longer conservative path and travel time. Lastly, our proposed method learns the predicted uncertainty of vehicle trajectory depending on the characteristic of terrain and computes the safe but less conservative path based on learned vehicle-terrain interaction given the 3D vehicle model. Here is the overview of our proposed method. We first introduce the environment with 3D terrain topology, as shown here, and the vehicle is equipped with 3D LiDAR and RGB camera in front. Based on the sensor measurements, we acquire 2 different types of maps. First, the geometric traversability map encodes the slope, roughness, and step height of the surface of the terrain. Second, we map the terrain types given the image-based segmentation module results. And given the processed terrain type map and the sampled control inputs, we generate predictive path distributions for each control input. We utilized a 3D vehicle model traveling along the elevation map and a learned vehicle-terrain interaction using the Gaussian process model for each different type of terrain. Then the generated predictive path distributions are used to compute the uncertainty-aware traversability cost by applying the kernel smoothing trick. The main idea here is we combine the costs of the expected geometric traversability cost along the predicted path distributions. Then the generated predictive path distributions are evaluated to select the best path based on the uncertainty-aware traversability cost, the risk of rollover, and distance to the goal. To track the given path, we utilize a sampling-based MPC method called Model Predictive Path Integral Control (MPPI). For comparative analysis, the left baseline method only considers the geometric traversability cost, so it enters the mud area and spins. The right video shows the baseline method considering the geometric and semantic properties of the terrain. It simply avoids mud areas, resulting in a longer path to conservative. Compared to the 2 baseline methods, our method sometimes avoids or drives over the mud area to make safe but agile navigation. The interesting point is that the proposed algorithm guides the vehicle to cross the mud area as it guarantees vehicle safety based on the predictive path distribution. This, in turn, results in a much shorter path than the others. We conclude this video by sharing the link to our source code.